Hello, everybody. Today we're going to talk about Chapter 7, Estimates and Sample Sizes. So in the previous chapters, we were given the population information, like the population standard deviation, the population mean. And in this chapter, we're going to actually learn how to estimate the population's parameters based on the statistics we get from a sample. Remember, if you think back, population deals with parameters, and a sample deals with statistics. So we're going to use statistics to estimate parameters. All right, so first we usually estimate a population proportion. We see that proportion represented as a percentage. So what percent of, let's say, what percent of college students in statistics are female? Well, we could estimate it using our class. Really, we can't, and we'll look at why not in a minute. But if we did, we have 13 students, and 5 of them are female. So our sample proportion would be 5 out of 13, which is about 38%. So some notation. P is our population proportion. So that's for the population. That's what we're trying to estimate. To do that, we look at our sample proportion, which is notated by P hat. This little caret above the P is called P hat. And it's the number of successes, in this case, the success would be being a female, and a sample size of N. And we also have Q hat, just like P and Q, 1 minus P hat gives you Q hat, and that's the proportion of failures. Now, why can we not actually use our class? Well, if we look at it, what kind of distribution are we dealing with? We either are female or we're not female. So success or fail, that's a binomial distribution. And we're going to actually approximate it with the normal distribution, like we did last chapter. So first off, first requirement is the sample is a simple random sample. And that's where we fail. Our class is all one cluster from a very specific population, people that go to Oberlin High School. So in this population, there's, perhaps tendencies for males to not go into statistics because they might just want to be welders, or they, might just make a farm. Who knows? But our population can't be estimated based on our sample of Oberlin High School because it's not a good random, simple representation of the entire population. That's where we fail. The other requirements in order to use this are, well, it's got to be binomial. So if we look at it, we know there's a fixed number of trials. Each one's independent, and it either succeeds or fails. Also, there has to be at least 5 successes or failures, and failures. And we're going to estimate that by doing n times p is greater than 5, n times q is greater than or equal to 5. So here's a summary of that for your notes, make it a little easier. Got to be a random sample. Fixed number of trials, they're independent, either succeed or fail. The probability is constant for each trial. So it's not a varying probability for being a female. If you're female now, you'll hopefully be female tomorrow. N times P is greater than or equal to 5, N times Q is greater than or equal to 5. That's the last thing you have to test to make sure we can actually approximate it with a normal distribution. So what we got was a point estimate, that 38%, right? This is what our sample says. They're going to be 38%. That's one value. That's a point estimate. Remember CDF and PDF? Well, PDF, point estimate, that's what we're looking at. Now the problem with that is it gives us a percent, but how good is that percent? How close to the real thing is it? And that's where we need some confidence. We're going to look at the CIA. Well, actually, that should be an alpha, not an A. Honey there. So confidence intervals and alpha. A confidence interval is a range of values used to estimate the population parameter. So it's a range that estimates the population parameter. Okay. So we're going to calculate the confidence interval, and it's going to tell us our population parameter somewhere between this value and that value. Might be between 0.1 and 0.3 or something. We don't know. We'll find an interval to estimate our population parameter. Now, directly related to that is the confidence level. That's how sure are we? Like on the last thing, we had the point estimate. We didn't tell us how good that estimate was. The confidence level tells you how good your estimate is. It is 1 minus alpha. We'll talk about alpha in a second. And it is the proportion of times that confidence interval actually contains the population parameter. So if we do the exact same number of trials over and over and over again, whatever our confidence level is, that'll say, like, okay, 95% of these estimates contain the actual population parameter. And usually our confidence level is either 90, 95, or 99%. That's the most common ones. It could be anything, but these are the common ones. And those correspond to an alpha value of 10, 5, or 1%. Again, it's a probability, so it's between 0 and 1, and the confidence level and alpha are just complements of each other. So how do we interpret a confidence interval? So some statistics were done, and we got a confidence interval to estimate the population proportion, P, as somewhere between 0.381 and 0.497. So here's a correct and incorrect interpretation of it. It's not a 95% chance. That's not what the interval means. What it means is that 95% of the time, if we have the same size samples that we're looking at, 95% of those large, how many ever samples we have made, 95% of them would actually contain the value for the population proportion. So it doesn't say that it's 95% chance that you're going to have P in here. It's saying that if you do this same number of trials many, many times, 95% of those trials will actually have the population parameter in there, population proportion. To do anything with confidence intervals, we need to look at the critical values. So the confidence interval is saying we're somewhere between here and here. Well, the critical values are those cutoff points. It's the borderline that separates the statistic that's likely to occur and those that are unlikely to occur. And if you look at it, Z of alpha over 2 is the notation. Z for Z scores, we're looking at Z scores again, and alpha divided by 2. Why do we divide it by 2? Well, this is our confidence interval. So if our confidence interval will say 95%, then 95% is between this value and that value. Well, what's on either side of it? Well, it's got to add up to 5% because it has to be 100% altogether. So half of 5% goes over here, and half of 5% goes over here. That's why we divide the alpha value by 2. This is actually known as two tails. Whenever we get to hypothesis testing, we'll talk a lot about left tail, right tail, and two tails. But for now, all we're going to be dealing with is a two tail since we're dealing with a confidence interval. So we're always going to be dividing alpha by 2 for these confidence intervals. So let's practice. Let's find the critical value, V of alpha over 2, corresponding to a 95% confidence level. So I got my curve here. So somewhere between here and here. Let's say that this, all this, is 0.95. So what are we going to do? Yeah, you get the picture. Pretend that's all shaded. Is find these z-scores. If this is 0.95 in here, then 1 minus 0.95 gives me alpha. This is my confidence level, minus 1. Confidence level The confidence level is 0.95. So alpha is going to be 1 minus 0.95, which is 0.05. Chop that in half. So right here, this would be 0.25. Sorry, 0.025. And right here, that'll be 0.025. Each one of them have to be half of alpha. Now these z-scores are going to be the same value. Just one's going to be positive, one's going to be negative. Let's look it up. So I want 0.025 to be to the left of my negative z-score. So let's look on our chart first. So it's a negative z-score. And we want 0.025. 0.025. Oh, here it is. That corresponds to negative 1.96. So here's the 0.06, negative 1.96. That's what this is. To find this one, and to show that it's the same value, we have to get the total area to the left of this z-score right here. This is 95, or 0.95, this is 0.025, so we're going to look up 0.975. So we can get all the area to the left of this z-score. That's going to be positive, and it should be 1.96. Let's find out. 1.96 right there. Yep, 0.9750. And that'll always be the case whenever we're dealing with these confidence intervals. It's right in the middle, so it's going to look for the z-scores that are right on that border, right here. They're going to be the same value. Just one's going to be negative, one's going to be positive. Okay. Here's the common ones. We just found that for 95% confidence, it's 1.96. 90% confidence, it's 1.645. 99% confidence is 2.575. So we use these a lot. So if you want to just go ahead and write them down now, you won't have to look it up in the chart every time. Now, if we're doing this in the calculator, for the TI, it's just an inverse norm. For the first one, it was 0.25. Mean and standard deviation are 0 and 1. Negative 1.96. For the other one, we had an area to the left of 0.975. It was also 1.96. And again, you can just look up this alpha over 2 value and, that one's negative, that one's positive. On the Casio, we're going to go to our distribution. Number 3 is inverse normal, 0.025. And mean and standard deviation were 0 and 1, negative 1.96. Area to the right, 0.975. Oh, sorry, area to the left. Standard deviation is 1, mean is 0. There it goes, 1.96. So it's not too bad with the chart, but it's also very simple with either calculator. And in fact, you could just remember them. They're right here. All right, to construct a confidence interval, we need to find the margin of error that we're working with. So here's the formula for it. And if we look on our formula sheet, it's there. We're in chapter 7, right here. The margin of error is v of alpha over 2 times the square root of p hat times q hat over n. Well, just, write down your variables and plug them in, and you're not going to have any problems. Now, what is the margin of error? It's the maximum likely difference between your parameter and your statistic, your p and your p-hat. And this could be your x-bar and your mu also. It's margin of error. This formula is for proportions, but the concept applies for estimating the mean as well. Now, there are rounding rules, and we're supposed to use 3 sig figs. And I know you don't know what sig figs are, so here's what it is. Your answer is going to look something like this, 0.123. Or it might look like 0.0123, or 0.000000123. The important thing is that you have 3 decimals after the last 0 to the left. So here's the last 0 to the left, 1, 2, 3. It could also be 0.100, or 0.110, or even 0.0101. So for sig figs, the zeros to the right of your decimal after your first non-zero digit are significant. Basically, the answer is going to look like one of these things. Make sure it does. If you get this from the calculator and you round to 3 decimal places as 0, I'm going to mark it wrong because it's not 0. You need to give me enough data to know whether you did the problem or not. Now, the confidence interval takes your sample, your statistic right here, your sample data, and subtracts the margin of error. Takes the sample, adds the margin of error. So this could be P, it could be X bar, either one of those will work. Just depends on what we're talking about. This, for today, we're only talking about proportion, so it's going to be P hat. So P is somewhere between P hat plus E and P hat minus E. So the way we construct these is first, make sure you can do it. Make sure it's simple random and all those other binomial conditions are satisfied. N times P is greater than or equal to 5, N times Q is greater than or equal to 5. Then find your critical value. However you want to do it, you can use your calculator, you can look up in the chart, whatever, don't matter. Then you calculate E, margin of error. So use this formula on the previous page, type in some numbers, and it spits out your answer. After we do that, we take our sample proportion, P hat, and subtract E, that's the lower bound, and we add E, that's the upper bound. That's going to give you your confidence interval. It's a range of numbers, P hat minus E all the way to P hat plus E. So let's look at an example. First, we're going to find the margin of error. This is on page 361, by the way. So, well, the chapter problem talks about this 4th grade girl that constructed a statistics experiment about touch therapy, and she got published. Here's her results. She had 280 trials, 123 were correct. So we're seeing if these touch therapists can detect the energy from your hand, basically. I'll show you what her setup looked like. Doesn't really matter for the problem, but there it is. So Emily here was conducting an experiment with touch therapists to see whether or not they could correctly identify which hand her hand was over. And here's the results. There were 280 trials, 123 correct identifications. So P hat is 123 out of 280, 0.439286. So that would be the point estimate we use. But again, we want a confidence interval. So we need to find the margin of error that corresponds to a 95% confidence level. Okay, so part A, E equals, let's grab our formula right here. Before I just start plugging in numbers, I'm going to write down my variables. So I need to find Z of alpha over 2. I'll look that up in a second. To do that, I need alpha, it's 95% confidence, which means alpha is 0.05. We need p hat and q hat. Well, need a little space here. P hat was 123 out of 280. I'm just going to leave it as a fraction because it's better than rounding. We don't like rounding, not until the end anyway. We need to keep our answers as accurate as possible, so we only round at the very end. Q hat is 1 minus p hat. If we do 1 minus this fraction, you can feel free to use your calculator or just subtract 280 minus 123. That's going to be 157. So let's see, what else do we need? We've got alpha, so we can look up v of alpha over 2. We've got p hat and q hat. We also need n. Well, n was the number of trials, which was 280. So here's my info. Use it to figure out what v of alpha over 2 is, so we can figure out what e is. Again, it's alpha is 0.05. If you remember, it's 1.96 for our critical value, but we can look it up again. Don't forget to cut that in half. Half of 0.05 is 0.025. If I'm using the chart, I'm usually lazy. I just look up the negative one. We're looking at 0.025. And right here, that's negative 1.96. So I know that my v of alpha over 2 is positive 1.96. You could also add the confidence level to half of alpha, 0.975. Look that up, and you'll still get 1.96. You can also use your calculator, and you'll get 1.96 because that's what we already did. You could use 0.025 and just take the positive of it. Doesn't matter which calculator you use, same way, same result. Now we can calculate our error, our margin of error. So we have our z-score is 1.96. Let me do this in red. Times square root p hat was 123 over 280. I need to extend my square root a bit. Q hat was 157 over 280. Divide that by n, which is 280, and see what we get. Let's see, I'll use this one. Go to mode 1. So 1.96 times. I'm going to use square root with a fraction side of it, 123 over 280 times 157 over 280 over, well, 280. And that should be my margin of error, 0.058, etc. So I need 3 sig figs. 0.0, that doesn't count, 581. There we go, that 1 stays a 1, so that's what I'm going to use, 581. And actually, I'm not going to round to the very end, so for the next problem, whenever I'm doing a confidence interval, I want that next digit. So I'm going to go ahead and put that 3 on there. So that way, whenever I round my final answer, to 3 sig figs, we should be all right. Shouldn't have any rounding errors to worry about. Now for the TI, if you're typing all that in, you have to use a lot of parentheses. So let me go through it. And in a minute, I'll show you why you don't have to type any of this in. So 1.96 times square root. And again, you're not going to have math type. Let me see if I can turn that off real quick. Let's see. Bear with me just for a second. There we go. Now look more like your screen. So 1.96 times the square root, that's what you should see, of, and anytime you have a fraction, put it in parentheses. I have an open parenthesis for my square root. I need an open parenthesis for my numerator. I need an open parenthesis for my fraction, because it also has a numerator. Oops. 123 over 280. Close parentheses for my first fraction, times, open parentheses for my second fraction, now, that's my entire numerator. I'm closing my parentheses for my numerator. I still have my parentheses for my square root open. I need to divide that by, put your denominator in parentheses, close the square root. Same thing, 0.05813, etc., etc., etc. Okay, so typing that in on the TI is a lot more cumbersome, but again, you're not going to have to. I'll show you how in just a minute or two. So that's a margin of error. Okay, so that's part A. Let me copy this, and let's look at part B. So for part B, it says find the confidence interval. So we found from part A that E was 0.5813. So we need to get the confidence interval. Look at your formula. Here it is. So all we have to do with that E is add it to our P hat and subtract it from P hat. So what was P hat again? Oh yeah, P hat was right here, 123 out of 280. All right, so if we take this value and add E to it, we get our upper interval. So it is an interval, so I'm going to put it in an interval notation. So you could actually, it would be better if you just use the answer key on your calculators. Just use that answer key so you don't have any rounding issues. So that's what I'm going to do. I'm going to say 123 over, well, I'll put it in fractions on this one, over 280 plus my answer. Okay, that gives me that. 0.497, 3 sig figs. So now we're going to round it to 3 sig figs, 0.497. I need to get my previous answer back, so I'm just going to undo what I did. Minus 123 over 280 gives me that back. You could, again, just use the 0.05813. It won't make a difference on this one. And now I need to do 123 over 280 minus, oops, minus that answer, 0.381366. So this is my interval. That's my confidence interval right there. Now, if you're on TI, you don't have to find the margin of error to find your confidence interval. You can go to stat. So let me start. Clear the hole. Right here, stat. We'll go to tests. We go all the way down to letter A. Well, I don't know what it might be different on the TI-83. This is on the TI-84. It should say 1-prop Z int. That stands for one proportion Z interval. That's what we need. So find one prop Z int on your calculator. And it's going to ask you, what's X? Remember, the number of successes is X. Total number is N. 123, 280, confidence interval is 0.95. I did this one earlier, that's why it's already in there. And you just type it in, it spits out your answer. 0.381 to 0.497. Done. So if you actually needed the margin of error, like for part A, what you could do is find the interval and then just take your upper bound here, 0.497, and subtract P. And that'll give you your margin of error. Now, if you see it's a little bit off here, that's because of the whole rounding thing. It would be better if we went 0.49742, like it gives us. And that should get us closer. There we go, 0.05813. So don't round until you absolutely have to. That's why we use sig figs. We do it a lot in science, we have to do it in statistics. But notice how when we just did 0.497, we got a significantly different margin of error than if we actually used everything we were given. So now our margin of error matches since we used all 5 decimal places. We went further out than the original. So we're good to go now. Based on the results, what can we conclude about the effectiveness of touch therapy? Well, what do you think? So we are 95% confident that their success rate, if we do this if we grab 280 touch therapists or do 280 samples from different touch therapists, 95% of the time, we're going to get that parameter. And it's going to be somewhere between 0.381 and 0.497, according to this. If it was successful, I'd expect it to be a lot higher. I mean, this is less than 50-50, so just plain guessing should get you 50-50. And this is saying no, they suck. You know, I mean, maybe 80% I could say, oh yeah, they might actually be able to sense your energy. Here, they're saying nah, they don't know anything. They're just making stuff up. And they actually published the results in a journal. Let's see. This one. Yeah. So here's what they wrote. The touch therapist's failure to substantiate touch therapy's most fundamental claim is unrefuted evidence that the claims of touch therapy are groundless and further professional use is unjustified. Basically, they suck. And I don't remember if we went through the conditions, but it should be obvious to you that n times p, since 123 is greater than 5, and N times Q, where we looked at it earlier, was 157. So both are way above 5, so we don't have to worry about it. It's good to go. Now, what if we know how confident we want to be, and we want to find out how many people we actually need to test to be that confident? So we're going to call that number of things or people N. That's our number of trials. And here's the formulas. We just did some basic algebra and rearranged for N from this formula right here. Basically, they took this formula and solved for N, and they printed it out for you. Aren't they nice? Again, it's on your formula sheet somewhere, right here. Again, the first section in Chapter 7 is dealing with proportions. And we have two different formulas to calculate the proportion, to calculate N for the proportion. If we know P hat, well, if we know P hat, we also know Q hat. So if we know them, we multiply them together, P hat times Q hat. If we don't know them, we assume they're both 0.5. 0.5 times 0.5 is 0.25. So if we have no sample data, and I mean, if we're about to construct an experiment and we want to know how many people we are, we haven't already constructed the experiment, right? So we use the 0.25 to get that sample size we need. Now, if we're repeating the experiment, then we can use the previous data to construct a new sample size. All right, so there's the two formulas. Let's try and use them. So, the ways that we communicate have been dramatically affected by the use of answering machines, fax machines, voicemail, email. Yeah, so this, as you can tell, this book's kind of old. Who has an answering machine anymore? We have voicemail. Suppose a sociologist wants to determine the current percentage of U.S. households using email. How many households must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 4 percentage points? Also, they didn't say text, so yes, it must be really old. So let's write down what we got. Our confidence interval is 95%. That means alpha is 0.05. And just by memory, that means z of alpha over 2 is 1.96. If you don't have that in your memory, do an inverse norm. Don't forget to cut off in half. Let's see, what else? It tells us our error is no more than 4 percentage points. So error is 4 percentage points. So 0.04. Always make sure you convert your things to a decimal. That way they like to work together. Part A. They did a study before. They found P hat was 16.9%. So again, convert that to a decimal. And let's go back to our formula. Let me just take a screenshot of it. We know P hat, so I'm going to use this one. So let's see if we have everything we need. You might know something's missing. Let's see, z of alpha over 2, we got that. P hat, we got that. Uh-oh, we need Q hat. Well, how do we find that? Remember, Q hat is 1 minus P hat. So that's going to be 0.831. 1 minus 0.169. So now we got P hat, Q hat, E, and Z alpha over 2. We got everything we need. Let's get it done. Just shove it in there and see what it spits out. And let me change the color. So now we're getting to work. 1.96 squared times 0.169 times 0.831. Now, there's no shortcut for this on either calculator, so just got to write down your variables, plug them in the formula. Error was 0.04. Don't forget to square it. I do that sometimes. And I'll show you on both calculators, starting with Casio. Again, if you need to get the 1.96, you're just going to do an inverse norm. Inverse norm 0.025. Use the positive of it and you're good to go. Squaring it so it doesn't matter really. Fraction. 1.96 squared times 0.169 times 0.831 over 0.04, and don't forget the squared. That gives us 337.19. Now, for rounding these, to round the number of people, we're always going to round up. Sorry, baby's crying. So that means 337.2 would round to 338. It doesn't even matter if it's 0.0001. Now, if it's a whole number, you're going to just leave it as is, but it's unlikely that you get a whole number out of this. So always round up. Regardless of what the decimal is, go up. Now let's see what the difference is if we didn't have any previous data. Oops, I think I already have this saved, don't I? Yeah. So that's not the form we're going to use. We're going to use this one. So now we're looking at B. Assume that we have no prior information suggesting a possible value for P hat. So we're going to do the same thing, same values, except we don't know what P or Q is, so we're just going to use this info. So this hasn't changed. Alpha is 0.05, which means Z of alpha over 2 is 1.96. That's what we're going to use. And E is 0.04. So we do 1.96 squared times 0.25. Again, the 0.25 is assuming both P hat and Q hat are equally likely. 50-50. 0.5 times 0.5 is 0.25. And error right there. I'll use the TI this time. Again, always put your numerator in parentheses. Don't forget to square things. Divided by, put your denominator in parentheses. And don't screw up like that. Squared, then close parentheses. 600.25. Again, we have to round up. So that would suggest N is 601. So if we had no data, we'd have to go out and grab 601 people, and that would be like, okay, now, let me check on this. Now you can be 95% confident with your 601 people. I think my wife just woke her up opening the door, but let's see. Okay, she's good. Sorry about that. Now, what if we know the confidence interval? Like say you're on TI and you already got it, but we need to find the margin of error and or the point estimate. Well, I showed you earlier how you could just subtract. It does, the TI does give you the point estimate whenever you're whenever you're finding the confidence interval. Oh, hang on a second, I'll be right back. Sorry about that. Just trying to climb out of the crib. Where were we? What if we want to know the confidence interval and need to find the margin of error? Again, the PI does give you the point estimate, so you could just subtract it. But what if for some reason the problem gave you the confidence interval? Well, to find it might be kind of obvious to you. We just average the upper bound and lower bound, and that'll give us right in the middle. That'll give us our midpoint, which would be our point estimate. Now, to get the margin of error, we could either take our bound and subtract that value we just got, or we could calculate the mid-range, upper bound minus lower bound over 2. And if you look at the formulas, the algebra works out. And let's see what we have here. So here's an example. Nicotine patches. Of 71 subjects, 70% were abstinent from smoking at 8 weeks. 95% confidence interval, 58% to 81% was the interval. Use this statement to find P hat and E. So here are our, that's our confidence interval, 0.58 to 0.81. That's our confidence interval. We want E, and we want P hat. So E, we calculate the mid-range. Upper minus lower divided by 2. And let's just look at the formula for a second. Let's see why this works. Careful with the door, you woke her up. Careful with the door. So if we look at the formula here, it's P hat plus E and P hat minus E. So if we're subtracting them, the P hats will cancel, and we'll get 2 E's. Cut that in half, and we have our 1 E. She can't get out of the bed, Mommy. It's not done with nap time. So do that, and then divide by 2. 0.115. And same way we can look at the formula and do the algebra. If we add these two together, the errors cancel, and we'll have 2 P hats. Cut that in half, and we'll get our value. So 0.81 plus 0.58 divided by 2. Yeah, when you open the door, I think it caused the giraffe to woke her up. Oh, it was whenever you opened the door that she started hollering. So add those together and then divide that by 2. 0.695. I have none. So p-hat was 0.695 or 69.5%, which they rounded to 70%. So there it is. There's the margin of error and the sample proportion based on the confidence interval. And that's it for today. So I'm going to post some homework. Tomorrow I'll go over the solution for them. And then the next day, we're going to talk about estimating the mean. This lesson was all about estimating the proportion. So next time, we're going to talk about the mean.